In this video, we're going to talk about diagonal matrices and diagonalizable matrices. So let me give some context here. So in general, if we want to compute a power of a matrix, a to the k, that's tedious. But there are special cases of matrices, I'm calling them special classes of matrices, for which this is actually easy to do. But let me briefly talk about why is finding the power of a matrix tedious. So if I had like a 2 by 2 matrix, A, B, C, D, like this, those are the entries, and I just square it and multiply it by itself, I have to sort of do the row column rule to multiply this out. But one thing for sure that's not true is this is definitely not just equal to A squared, B squared, C squared, D squared. It's definitely not just equal to that, because there's a lot of complicated row column multiplications that are going on. And if I wanted to do a higher power, well then I have to do this tedious multiplication every single time I tack on another matrix. Okay, but luckily for us, there are some special classes of matrices for which this raising a matrix to a power is easy. So the first type of matrix for which this is easy is what's called a diagonal matrix. The second type of matrix that we're going to look at for which raising it to a power is easy is what's called a diagonalizable matrix. Okay, so let's first define what a diagonal matrix D is. So a diagonal matrix D is a matrix that has the form where there may be some diagonal entries. So I'll call those D11, D22, up until DNN. So there's some diagonal entries, but then everything that's not on the diagonal is 0. So the things both that are above and below the diagonal are 0. So there may be things on the diagonal that are non-zero, but everything that's not on that main diagonal is 0. So that's what a diagonal matrix is. So let's do an example. Let's say that D is this diagonal matrix, 2, 0, 0, 3. Now let's compute D to the 100 and see that this is actually easy to do. Okay, so let's begin with D squared, which is going to be our matrix times itself, 2, 0, 0, 3. And if we do the row column rule to multiply this, so I'll do it slowly for the first entry and then a little bit more quickly after that. So I would do 2 times the 2 and then 0 times the 0, and that gives me 2 squared. And if I keep going like this, the next entry underneath that is 0. The top right entry is also 0. And then the bottom right entry is going to be 3 squared. So that's kind of nice. If I wanted to raise this to the second power, basically what happened is each of these diagonal entries got raised to the second power. Okay, if I did the same thing and I cube this, so if I multiply this matrix by itself one more time, it turns out I would get 2 cubed here, 3 cubed on the next entry, diagonal entry, and then the others are 0. And if we keep going like this, the pattern is that D to the 100 will be 2 to the 100, 0, 0, and then the other entry is 3 to the 100. So that's what D to the 100 is. And we don't need to worry about actually multiplying out these numbers, like 2 to the 100 or 3 to the 100. It's fine to leave them how they are. Okay, so let me state another definition. So 2 more definitions, in fact. So the first definition is that two square matrices, A and B, are called similar if A equals P times B times P inverse. So if A has this interesting looking form for some invertible matrix P. So if we can express A in this form, then we say that A and B are similar. So in this special case that A is similar to a diagonal matrix D, so what that would look like is if A equaled P times D times P inverse, then we call the matrix A diagonalizable. So a diagonalizable matrix is a matrix that can be written in this way, P times D times P inverse, where P is some invertible matrix. So let's do an example raising a diagonalizable matrix to a certain power. So let's say that A is going to be P times D times P inverse, and I want to compute A to the 100. where D is the same matrix that I had before, the same diagonal matrix, and P is this matrix 2 by 2 that's invertible. And if I have a 2 by 2 matrix, I can quickly see that it's invertible because the columns are not multiples. So the columns are linearly independent. And just for review, I've written down the formula for the inverse of a 2 by 2 matrix. And that's how I got this formula for P inverse. I don't want to spend too much time focusing on the details of that. We've talked about this before back in, I think chapter 2. Chapter 2 is when we talked about the inverse of a matrix. Okay, so this is how I found the inverse of P. So I want to focus mostly on, well, how do I use this now to compute a to the 100? So I'm going to first compute a to the 3 and see if we can establish a pattern, and then do a to the 100. So if I do a to the 3, well, I have to multiply the matrix A by itself 3 times. And A is P times D times P inverse. That's A. That's A. And I have to multiply that by itself 3 times. Let's do another A, and then let's do another A. So the next A, P times D times P inverse, and then again, P times D times P inverse. So there's something that we should notice about multiplying all of these. A few nice things happen. We know what P inverse times P is, and it shows up twice. Multiplying a matrix by its inverse gives us the identity. So that's the identity, and this is the identity. So then when I multiply D times the identity, well, D times the identity is just D. So we're going to have D times this D times this D. That's D cubed. So we end up with the fact that A cubed equals, we'll still have the P at the front. We're now going to have D cubed in the middle, and then we'll have this P inverse at the end. So I think at this point we could see that if we were to do this to a higher power, similarly, we would get that a to the 100, if we multiply that out and get all of its cancellations, we would get P times D to the 100 times P inverse. So that's what a to the 100 would be. It would be this matrix right here. And at this point, we could plug in and multiply this out if we wanted to. I'm not going to do that in this video, but if we needed to do this multiplication for some reason, we definitely could. I mostly wanted to focus on, well, if I have a diagonalizable matrix, something of this form, what does a power of that look like? And now we've determined that.